Funding for this podcast is provided in part by the IPM Network through the USDA National Institute of Food and Agriculture and by various commodity groups through checkoff dollars, including the United Soybean Board, National Corn Growers Association, and Cotton Incorporated.
The I See Dead Plants podcast shares the stories of people and plants, pests and pathogens, and the conflicts among them. Join us as we speak to the folks who attempt to solve complex problems with plants through pest management research. I See Dead Plants is an extension-based podcast created by the Crop Protection Network and the North Central Integrated Pest Management Center and hosted by Ed Zaworski.
So, I know from reading your publication, the complexity increases beyond machine learning, and there were a couple of different types of machine learning models that you guys were looking at, the SVM and the random forest. Do you want to give us like an overview of what those are?
With these type of models, it's hard to describe them because sometimes they feel like magic. They feel like basically you just throw in a bunch of things in a black box and then you have a really nice output of very useful stuff that sometimes it's hard to interpret because they usually handle and they work well with the large data sets. It's actually one of the requirements that you are expected to have when you use this type of models. But basically, for support vector machine, my understanding is that the variables that you feed the model into, it uses it to find the most robust boundary that explains how to classify the two groups that you're having. So again, if we have a 0 for, let's say, no disease and 1 for healthy plant, and then you bring in a bunch of variables that are related to that phenomena, it will compare all the variables available to find the most robust boundary to separate those classes. Then the random forest, it's a different approach because basically what it uses are decision trees. So the algorithm is designed to use the data set that you provide and randomly sample data points from that data set to build decision trees. But it uses a method called bootstrapping, which means that it can resample again and again from the same data set randomly to create different decision trees, which you can set up to be 500, 1,000, whatever you want, and you fine tune to whatever gets the best output in terms of accuracy or whatever metric you want to use. So yeah, that's the main difference between them. It's a support vector machine focuses on finding the boundary to classify the two groups. Random forest focuses on having a bunch of decision trees that then you can average them to find what is the most likely and accurate result for your data set. So you can have an interpretable output of some kind. Yeah. So
tell me if I'm wrong. Like this is just what I'm hearing, and I want to make sure I understand. Basically, back in the early days of modeling, before true machine learning, even though, like you said, a logistic regression model is technically machine learning, now it sounds like we're just able to supercharge it because essentially a human being doesn't have to sit there and tweak all these variables. A machine can do it at a really high rate and basically, I don't know. I mean, like that's the way that I understand like AI in general, right? Is like it can do things so much faster than a person. Like a person could eventually do these things, but it might take
in 1,000 years,
multiple generations of that person, and yeah, exactly. But this doesn't have to sleep, it doesn't have to eat. It's like it's a machine. Is that more or less what we're doing here with machine learning models in these two types of models?
I think it's a good description, coupled with the improvement in computing capabilities. Like, yeah, you now can do those kind of things that sometimes feel like magic because it will take us hundreds of years to solve. But now we have an algorithm that can run real fast and give you a result like this.
So when I was reading the publication, this was something that I was like, okay, I can't wait to talk to Jose because I didn't really understand. Because so I was reading that you had the SVM model in the random forest, and how did you ultimately pick which model you'd use for this system and this project?
In that publication, for people that go out and find it.
It'll be in the show notes. So if you want to
Great.
do the deep dive,
Yeah.
I highly recommend.
No, great. So I put together a table comparing the best models that we found after doing all the modeling efforts, and we were comparing a few logistic regression models to these two machine learning models, which kind of felt a little bit of that the logistic regression models were in a disadvantage because it feels like if you have to run against an athlete or something like that.
Yeah.
But at the end, the logistic regression models performed really well. In general, they had a very good performance. But anyway, the machine learning models had higher accuracy and higher sensitivity, which sensitivity can be seen like the capability of the model to detect true positives or detect when there is actual disease or disease increase. So they have that capability of having better performance. But again, the logistic regression models weren't that behind to the more complex machine learning models. Something that drove our decision of using the logistic regression models in this case was the lack of, I don't know what is the right word to use, but the decision support system that we have online does not support machine learning yet. Because with my understanding of this is that for example, the logistic regression model uses 1-2 variables max. It's a very simple equation, but so you can run it and it runs fine. But then when you bring in random forest that uses the Lord knows how many variables, and it's very heavy on computing, and if you need to have that in a website that has to run for anyone that comes in and click, and you have to draw a lot of environmental data to run only one model so it will be too much. So it's a more matter of an IT problem, but it would have been really nice to test them in the field, because I'm fast forwarding a little bit, but we went out and did some field validation of these trials, and there's another publication coming on that sense that I don't think we're going to cover here, but down the road it will be really nice to test those models real time, and hopefully I think the computing capabilities are there. There's just a learning curve that we have to go through.
So I kept seeing the words sensitivity and specificity with regards to these models, and I still don't understand what those things meant in the case of models. So like, what do those words mean with regards to either the model or the frog eye leaf spot system itself? Like,
sensitivity and specificity are two metrics that are very commonly used in developing predictive models and validating models in general. They are basically the proportion of times that a model predicts a true positive correctly or a true negative correctly. Sensitivity, for example, is the proportion of true positives that the model got right. Specificity is for the true negatives or no disease.
Oh, okay.
So it's just, they're two of the most important metrics that we use to make sure that our model is not way off.
So the ideal model would have high sensitivity and high specificity, in that it would be getting positives and negatives right.
Correct. Yeah.
Gotcha.
You got it. That's exactly right.
Okay, I understand.
Something that I think I haven't mentioned is that when we put together a model, when we have the data set, first thing that we do is that we split the data 70-30. So 70% of the data, we use it to develop the models and the equations that then we're going to use to test it against the 30% of the data that the model have not seen, because we don't want to test the data on the same data that you modeled, that you used to train the model. So that's where specificity, sensitivity, and accuracy become really important to know, okay, this model is good on sensitivity but very low on specificity, or the other way around. So you want to find a model that is balanced and that it's good at predicting both cases. Because at the end you will have like the real observations, again, thinking on coding the diseased on healthy plants as 0 and 1s, and then you have the predictive outcome from the model. So at the end you compare those two and get these metrics that can help you decide which model is the best. And again, it ends up being a little bit of an art combined with science, because then you have a few metrics, and there's a lot of metrics that you can use, but you select a few metrics, you run your models, and then you have to weigh what you're more interested in for what you need in your specific case for picking a model. For example, there was in my modeling effort, I think You can find it in the publication that there is another model different than the one that we picked as the best one for field validation that was very close to the one that we picked. And I think it was better on one of the metrics than the one that we picked. So at the end, I don't think there's like a right or wrong answer. It's more of a try to understand what is better or what is more appropriate to what you're trying to find.
Yeah, I mean, like what I'm hearing is like there's parallels to statistics, right? There's not just one way to one statistical model to pick that's going to give you the correct answer. You could attack it a bunch of different ways, but in this case, it sounds like, I mean, obviously you had to weigh in the DSS at the end, the risk tool that this thing would be on as far as what it was capable of handling, but also the sensitivity and the specificity.
Yeah.
And not just the sensitivity and the specificity, right? Because it needs to be a tool that's accessible too, right? So
exactly.
And so all that is basically what brought you back to using the logistic regression, right?
Yes, more like the possibility of implementing it into the decision support system. It also gives us a lot of confidence to use logistic regression because we have, well, people have been using it for a long time, so we are very confident on that it is a good approach to describing this kind of biological systems of disease and the interaction with a crop. I just want to say that the sensitivity, specificity, accuracy, these metrics, we use them to decide which model was best, but also we had other metrics that will tell a different part of the story. So it's kind of, we're using different metrics to look at the models from different angles to try to decide which is the best one. But we have different tools, statistical tools that we use in several steps of the process of modeling that will hopefully guide us to select the most appropriate model.
So I guess then, Jose, I wanted to ask you, I mean, we're talking about frog eye leaf spot in this case with this particular model set. Were there unique challenges that you saw with this disease system in creating a model?
I don't know if unique to frog eye, but in general, there were several challenges. I mean, this was the first time that I was in charge of developing a brand new model. Previous experience with the Apple project, I had an already developed model that I was then testing, but in a different setting. I was just using different products and different Apple cultivars. But then in soybean, it was like, well, we are a huge group of plant pathologists that have a lot of data, and we can give you all of that data, and then just good luck. Well, not good luck, but go and work, right? And I want to give a shout out to Dr. Wade Webster in North Dakota, because he was one of the main mentors that helped me went through all of this and navigate all of this project. And it was challenging to start putting together the data set without having a clear idea of what we really needed. So I started collecting a lot of data from all of the data sets. So I got emails, and I was fortunate to have access to a lot of data from a lot of different states. But each person does things differently. Each research group has a different format. Each of them report things in a way that they are saying basically the same thing, but it's a different formatting, and it's just the nature of each research group. Yeah. So in my case, I had to be very patient and go one by one, put together a data set that was a standardized data set that talks about the same thing that I want to extract from all of those data sets. So I think that was one of the main challenges. And now, lately, I've been reading a little bit more about the AI agents world. And I was thinking, well, maybe in the future, you can just program an AI agent just to do what I did that I suffered through. And that could be an interesting approach for future modeling of efforts. Just give a nice prompt to an AI agent, and you just go and review it. But in my case, I spent a lot of time putting together that data set, which was the one that at the end we used for the modeling efforts. One of the other challenges that I found was that sometimes you think that more data is always better, but in my case, I was able to access a data set that was from a different group that I incorporated into the whole data set that I had. And when I run the models, the performance of the models went down. So although I included more data, the capabilities didn't improve. So I had to run some comparisons, and at the end, I had to make a tough decision of leave out a bunch of data that might be useful for other stuff, but for this particular case, it was bringing down the capabilities of our model, of the models that we were putting together. So that was a challenge. That was a nice learning experience. I think that those two were the main challenges. But gladly, I was blessed to have the guidance again of Wade and Damon, support from Darren, and a lot of really nice people that helped me go through it.
It's crazy that, you mentioned earlier, like with a logistic regression model, you're translating things for a computer. But it sounds like you had to do like the human to human translation first to make a cohesive data set, and then put it in terms of the computer. Yeah. I'm just kind of curious, Jose, like what that data, you had this big data set, like what were some of the variables that you were putting into the model with regards to frog eye leaf spot? Was it all like leaf moisture and what were some of those?
Yeah, so actually that's a good question, because it gives me the opportunity to mention that for our modeling approach, we focused only on the weather conditions, weather data. And it is one of the main drivers for disease in most cases. But we were assuming, or we left out components that could be important for the disease. So this is just a comment that for future efforts, hopefully there are some incorporation of agronomic components, or for example genetic resistance to different cultivars, or geographical landscapes or different regions. So there's a lot of things that can be improved. But I'm very, very proud of the model that came out, because it's the first time that we are trying to model and validate this for the whole of the US. So it's not perfect, but I'm very, 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 very proud of it. But where I was going with this?
What were some of those variables? Like, you mentioned weather.
Yeah. So we basically had all of the weather variables that we could get from a company from IBM, that they have a weather database that it seems to use NOAA's dataset and other inputs to fine tune and give gridded datasets of environmental variables for a given location and date. And so we could pull out weather information for relative humidity, temperature, rain. We did a calculation for a variable that it's a proxy for leaf wetness. We had wind. Then we had different categories. So, for example, for relative humidity, we know that is very important for disease. So we looked at number of daily hours or average daily hours of relative humidity above 70%, 75, 80, 85, 90. So we looked at a lot of different components that could be a lot of different variations of all of these variables that could have an influence on disease. And we also did another level of timescales that it's called moving averages, which is nothing new. It's been used a lot in epidemiology, which is basically that we have a date of an observation. Let's say that we had an observation of frog eye severity. So we know that date, we know the location. So we will pull out the weather data, looking at the average of 5 days before that observation. But we did was 5, 7, 10, 14, 21, and 30 days before that observation that we have record of. In general, we tried that just to try to pin down what is the time frame where the environmental conditions might have an effect on disease development. So we looked at a whole bunch of the weather variables at different time intervals, and then from that huge list of models, so we fit a model for all of the variables. We tested, we used several metrics to pick the best ones, and then the best ones went to the next stage of testing against the dataset that I mentioned earlier. And then the next step was validation, which happened in 23, 24, and 2025, which is another paper that is coming out hopefully soon.
So I'm kind of curious too, along the lines of the data for frog eye leaf spot itself. Did you have like, because obviously this is multi-state. Were people just saying like, I had frog eye leaf spot in this county, or was there an element of severity or the progression of the disease over time at all, or was it just yes or no, or what?
For this particular data set, what we had was soybean fungicide efficacy trials from different research groups. So what we had was a small plot experiment with disease observations from 2015 through 2024. Different groups have different data sets that were shared to us. So what we had was severity percent, in most cases severity percent of frog eye. So what we did was to compare between dates of observations. So we could code the response variables as a 0 if there was no increase or no disease at all, and we will give it a 1 if between the observations that are reported in that experiment, if we see an increase. So in our case, it was a plot level evaluation of someone looking at a plot and estimating severity of frog eye.
So I think at this point, it's finally time to bring it back to, I've already forgotten the acronym, the DSS, but remind me, what does DSS stand for again?
So Decision Support System. DSS
yes.
It's a Decision Support System. It's a tool that you can use that organizes information, and usually they can be predictive models or any other type of model that can be useful in this setting for a farming operation. So there's this concept, for example, of a decision support system that can be applicable to all aspects of a farm. So an idealistic DSS could be a tool that you go in, and there's companies working towards that you could go in, and it will, according to the needs of your farm, it will tell you the irrigation needs, fertilization needs. A DSS can be for anything, like herbicide needs or weed management needs in general. In our case, we're talking about a DSS for disease management. So you could put, if you have a crop that has 3 major diseases and you have the models for each of those diseases, you could have a DSS that you could go in and have interpretable information that it's ready for you to make a decision. So, for example, like what I said earlier, that we have the predictive model for frog eye. Then if you go to the crop risk tool website, which is the version of a decision support system, it will give you the percentage risk of frog eye leaf spot severity increase in that location at that date. So from there on, it's up to a human or to a person to decide what to do with that. And going back to my comment that this is not a silver bullet, it's very useful, but it's not a silver bullet. In this model, we're talking about environmental conditions that are conducive to disease according to historical data that we have. But it is very important to consider where you are. If you are in a region where frog eye is really a problem, or if you're in a region that it's not a concern, or if the seed that you bought it's said to have resistance to the disease, then you probably don't need to worry much about it. Or if you are in a region that the conditions are conducive all the time, and you have a susceptible seed, for example, then these kind of tools could be very useful for you to make a decision, similar to the tornado warning, the example that we were talking about earlier.
So Jose, I kind of want to, at this point, transition into kind of the wrap-up questions at the end here. And I've been excited about this one since probably like the first 15 minutes after we first started talking about it. But the original question that I wrote was, what do you think the future holds for predictive modeling?
Mm-hmm.
But all this talk about decision support system also has me wondering about the future of that. What do you think the future of these tools is?
I'll start with the future of the predictive modeling. I think the first thing that comes to mind is validation. So we have had several models for different pathosystems in the past, but the agricultural landscape is changing, the climate is changing, new cultivars, new hybrids are used. So in general, I think that we, as a community of plant pathologists, we need to focus on validation and make sure that our models are still, good for what we have out in our fields. Because even recent, like it depends on the cropping system. But for example, in soybeans, the cultivars change a lot, so the genetics can change a lot. The same with corn. In other crops could be different, but with such type of cropping systems that are like that change a lot in terms of the genetics that we use, it's very important to keep running validations to make sure that we're fine tuning, or if we need to develop new models, we'll just go ahead and do run new efforts to get updated models. The other thing that I think is coming is the more and more implementation of these complex machine learning algorithms. So again, random forest, super vector machine. As we're speaking, there's probably like 10 new models that are coming out. So it's a very dynamic area. I think I'm excited to see what people will do with these tools. I read a very interesting paper recently that they are suggesting that these machine learning models can be used as an exploratory tool. So instead of substituting logistic regression models as the final model to use and implement it into a decision support system, they suggest that we can use a machine learning algorithm to find what are the most important variables in a dataset that could be used into a logistic regression model that are more relevant for a disease. So that's a really, really interesting approach that could be followed. Also, we could develop, use the models that we already have, like the ones that we found for Frog Eye, and actually run validations in field. Again, we will need a improvement in computation capabilities, and I don't know if those things can run in our current phones, which is something that we like about the crop risk tool, that you can just open your phone and just run it. You don't need a computer or nothing fancy. So I think that's coming. The other thing, now changing to decision support systems, is that, well, there are efforts both in public sector and private sector to develop decision support systems. Large ag companies have already their own apps that farmers can use to consult several things that basically is what I mentioned earlier, like fertilization needs or irrigation needs or risk of a disease from occurring. So they are already working on that. And then in the public sector, we're also developing our own models. But I think that, well, I'm not sure, but I think that the private sector is probably closer to developing decision support system, at least for soybean and corn, closer to what I think it needs to have, which is economic components, several aspects of the agronomic production. I guess one of the limitations that we have is in academia is that we are separated by topics. So we are plant pathologists, so we don't think of the weeds, for example. So that it will be nice to see some interdisciplinary work to put together these kind of tools, and at the end have the farmers or the farmers decide which of those systems are most appropriate or most accurate, or they just like most. Because I think there's something else that has to happen, which is constant surveying of the end users to make sure that what we are doing research on and what we're putting together makes sense to them. Because sometimes we just go all in the nerdy aspect of things, and we forget about the objective or the end of what we're doing. So
I often do this at the end of these podcasts, but I can't help it. I hear all these things, and I start to think of the like the Jetsons future. There's so many instances where people try to predict the future. In a lot of cases, they were very wrong. Like the Jetsons thought we were going to be flying in cars and stuff. But then sometimes it's eerily right, the predictions of the future. But
True.
In the case of this stuff, like, okay, this is pure speculation. Just have to put the disclaimer out there, folks. But if you had a crystal ball, like, do you think that, with machine learning and advances in technology and computing power, do you think that we get to a point where models are very accurate to the point where, maybe we have a decision support system that's just like bulletproof, the proverbial silver bullet, right? Like, do you think that it gets to that point, or are there always going to be issues with models, no matter how good of computing power we have? This is not a question that anyone actually has an answer to, right? But like, I don't know. What do you think about that?
Well, it makes me think on all of this, like if there was a final destination, but it's never gonna. We always will have to keep checking our models, improving them, and fine tuning them. So I think we will get better and better at it, and we have better tools and better computing power, and better understanding of how things work. And well, sometimes not, but at least we have improved models that are very good at predicting something that we're interested in. So I think that we're going to keep getting better and better. Hopefully we get to a point where we have a decision support system that makes life easier for farmers, which is one of the populations worldwide that suffer a lot because of the uncertainty of their operations. I'm talking about economic constraints, even mental health issues. So I hope that we are getting closer and closer to that scenario where we have a tool that can ease things and make life a little less difficult and help our farmers out there.
You know, there's a lot to unpack there, but I was thinking as you were saying that, perhaps we will never have a perfect model though, because it's a constant arms race, to quote Jurassic Park, right? Life finds a way. Like, even if we had a perfect model, climate's changing, pathogens are evolving, genetics are changing on plants, and I don't know that we'll ever have all of the variables that we'd need to put into these models to make it perfect. But if, like you just said, if we have something that's enough to help and reduce the stresses on growers, I think that brings me to the question that I wanted to ask you perfectly, which is what does a farmer or someone at a co-op that's advising a farmer stand to gain at this point from these models? Like, what's the benefit to them at this point?
Well, I will say that there are two main aspects that I can think of. The first one is economic. So if we have a decision support system that we can use to avoid doing a fungicide application, for example, or any other kind of farming activity that implies an investment, a cost, we could see savings for growers. So that will be something positive. On the other end, if we have a decision support system that tells us, well, there's a lot of risk of a disease from happening, you should spray, and then you spray and you protect your yield, then that's another benefit in terms of the profits of farmers. And the other component is the prevention of the reducing the risk of fungicide resistance from arising, because this is a whole topic on itself. But I already mentioned it, that one of the tactics that we can use to reduce the risk is to apply less fungicides or do less frequent applications on a given fungal population, so they have less of a chance to developing a mutation that will grant them resistance to the molecule that we use to control them. So I will say that those are the two main aspects that I think will make a farmer appreciate, or a co-op, or anyone involved in agriculture appreciate a decision support system like these ones.
Yeah. I'll put the crop risk tool in the show notes, a link to it. If you haven't checked it out, definitely check it out. As Jose said, it's going to be a rapidly evolving tool to be using in the coming years. Like you said, there's people working on all kinds of models right now. And that's what we know about in our field, right? Like you said, I know there's people working on models for weed management, insect management. So that's the cool culmination that I can see, is hopefully one day we get a decision support system that brings those things together. But Jose, that brings us to the final question. The elevator pitch, right? If you had to wrap this up for somebody, when you go home to Costa Rica and you're talking to a family member and you're trying to explain this to them in a short term, maybe a few sentences. How do you sell predictive modeling to them or a member of the public?
Well, I think that I will use like an example of not related to agriculture, like if we know the past, if we know about the past, we can avoid making mistakes that we have done in the past. If we have that information, then we have developed, say, a mental model or a mathematical model to make better decisions. So I will say that extrapolating that to predictive modeling for diseases, if we have access to some kind of knowledge, say theoretical or empirical, that we can put together some equations to predict something, well, that's a very useful thing that we can use for making better decisions into the future. So I don't know if that's a good elevator pitch, but that's what I will say.
For a second, I thought you were going to bring it back to the tornado warning.
Oh man, that would have been awesome. Man, I should have done that.
but it's still there. So, and I'm going to be trying to unpack that and think about that a lot, because there's so many parallels there. But with that, Jose, I like to leave time here at the end for you to make any acknowledgments, point people to any resources. You got the floor here. I'm done questioning you.
Thank you, Ed. Well, first thing I want to say is that I'm very grateful with a huge list of people. If you see the publication that's going to be linked in the episode, there's like 20-something authors. So it was a massive group project. But I want to shout out to Dr. White Webster. He was the main mentor on all of this modeling experience. Also, I want to acknowledge Darren Miller for hosting me and supporting me all this time, working in his lab and doing a PhD, and all the other researchers that have been part of this effort, part of the pipeline. One of them, Damon Smith, which is one of the key actors in this group that's been crucial to making all of this decision support system a reality. He has a great team in University of Wisconsin-Madison that put together these awesome tools that can be used by anyone in the US just by going in and doing a couple of clicks. Also, well, there was a lot of funding agencies from all around the US, state, and nationwide. Also, I don't want to leave out Dr. Gleason, because he was the reason that I came in the first place to Iowa State. So it's incredible what it can happen when someone gives you an opportunity. I'm very, very grateful with him, and I'll always be. Yeah, there's been a lot of people that have been crucial to making all of this possible, and I'm very grateful for all the support.
With that, folks, this has been a really fun one for me, especially since it's in person with Jose. I hope you learned a lot about modeling along the way here, and keep listening, and we'll see you next time.
I See Dead Plants bridges the gap between plant science research and the impact it has on our daily lives. It is brought to you by the Crop Protection Network and the North Central Integrated Pest Management Center, which are both partially supported by the USDA National Institute of Food and Agriculture. For more information on today's topic or other pest management issues, check out our show notes, cropprotectionnetwork.org or ncipmc.org. Remember, this information is for entertainment purposes only. The statements made in this podcast should be interpreted within the limited context of the particular topics being discussed. Contact your state extension program for local information on pest management. For the full non-discrimination statement or for accommodation inquiries, go to cropprotectionnetwork.org/about. Music written and recorded by fellow plant pathologist Sean Toporek. Thank you for listening to I See Dead Plants.